So this is the second of our lessons in week 12 for a question and answer session for those who show up. So this is chapter 21. Which question was it again? Hello, which question was it again?
Number 6.
Number 6. So it says, what is the effect of concussions on the brain? Researchers measured the brain sizes of 25 collegiate football players with a history of clinician-diagnosed concussions and 25 collegiate football players without a history of concussions. This table shows the statistics. All right, so they have the same sizes, different means, different standard deviations. Is there evidence of a difference in mean brain size between football players with a history of concussions and those without? Is there a difference greater than or less than? So this is a not equal to situation, right? So the null hypothesis is that the mean of the concussions is equal to the mean of the non-concussions versus the alternative that they're not different, correct?
Yeah.
Okay, that part was hopefully easy. Find the standard error and t-statistic for these data. So what we can do is we can open Crunch it. How do I just straight up open Crunch it? I probably go to the, let's open a new one. So here's Crunch it. Okay, Crunch it is now open. I can close this one. Okay, Crunch it is now open. So we want to know if there is a difference. So statistics, T2 sample. We're going to use the summarized data. They're both 25. 5784. And oh, someone said something, which is yes, that's fine. Okay, and 6489. First deviation is 609.3. Second deviation is 815.4. We're not pooling. We're looking for hypothesis test with the assumption of 0, two-sided calculate. So it asks for the standard error and the t-statistic. Okay, rounded to 4 decimals. So the t-statistic, negative 3.463. They probably want more than that. So they probably want you to do it by hand because they want 4 decimals, or maybe the 0 was just a 4th. And they want the standard error. Now they gave you this, oh, well, this is the answer. The question is, how do you find the standard error? So what's the formula for the standard error? It's the square root of S1 squared over N1 plus S2 squared over N2. All right, so let's make sure we get the right answer. So 609.3 squared over 25. 815.4 squared over 25. Atoms square root them, 203.5803. Boom. Make sense?
Yeah, I just had on Crunch it. How do you know which thing to push? How do you know it's summarized?
Oh, because they don't have the actual data. If I had the actual data, I'd put in the data here and I'd have Crunch it analyze it, but I don't have the data. I just have the summary.
Right. Okay. Thank you.
Make sense? Okay. I'm gonna pause the recording. So I'm resuming the recordings. We can load it up again. Let me share my screen. And this is question. Sorry, which question was it again? Which question was it again? Hello?
It's number 3, chapter 21.
Chapter 21, number 3?
Yes.
All right. So this question is based on summary statistics rather than data. Again, this information is typically all that is presented in published reports, right? They're not in published reports. They don't give you, all the details. They just give you the summary. Okay. So we have It says equip male and female students with a small device that secretly records sounds for a random 30 seconds during each 12.5-minute period over 2 days. And count the words each subject speaks during each recording period. And from this, estimate how many words per day each subject speaks. The published report includes a table summarizing 6 such studies, and given are 2 of the 6. Given are 2 of the 6. We have study number 1, 56 women, 56 men. Here's a woman's average, and here's the men's average. Study 2, 27 women, 20 men, women's average, men's average. And readers are supposed to understand that, for example, the 56 women in the study first had a X bar, an average of this, and a deviation of this. It is commonly thought that women talk more than men, and that's what we're going to test. Do women talk more than men? So the null hypothesis is that they don't, and therefore that mu female and mu male is equal. And what are we testing to see? Whether or not women are greater than men. Women talk more than men. So find the 2 sample t statistic for each study. So let's do the first study. In the first study, so it's a sample, it's a t, it's 2 samples, and we're going to use summarized data. So in the first study, there were 56 women and 56 men. The women's average was 16,177. And the men's average was, with a deviation of 75.20. And the men's was 16,569 with a deviation of 9,108. And we calculate. So it says, find the 2 sample t statistics. So I get negative 0.2484. Okay, there it is.
Thank you.
Okay. I'm going to stop. I'm going to pause again. Okay, so the question that was asked, can you ask the question again, Leanna?
So the question is, in a T or Z test, whichever, for the null hypothesis, how would you know when to use 0, which means there's no difference, or an actual number? Because sometimes they do give you a value and you plug it into like the p-value table where you try to determine it with software, but it gets really confusing knowing when to use 0 versus.
Okay, so this is a situation that the more you do, the better you get, obviously, like everything else. But in particular, it's usually the wording of the question that's going to indicate the answer to that. So if we're trying to determine whether there's a difference between men and women, or left and right hand, or morning and afternoon, whatever the case may be, the wording of difference means, well, if there's not a difference, then the difference is 0.
Mhm.
Okay, but let's say someone comes out with a paper that says that scores for afternoon classes are 0.4 points higher than scores for morning classes on average. And you say, you know what? I want to test that. I don't know if that's true. So in that case, what exactly are you testing against? You're testing whether or not it's valid that the difference is 0.4 or not 0.4. In that case, the null hypothesis, what you're going in with is that it's 0.4, and that's what you're testing against. So in that case, it'll be equal to 0.4 or not equal to 0.4 or greater than 0.4, less than, whatever the case may be. Okay, but the problem will give you an indication of what you're assuming going in, and therefore what you're testing against. Did that kind of answer the question, or not really?
It did. It made sense. I think it's just looking at the question of whether you're testing if the alternative and the null should be the same versus you're testing specifically for a particular null.
Exactly. That's what it comes down to being. Okay. If the status quo, if until then it's been that, oh, the difference is this, and that's what I'm testing against, then that will be my null hypothesis.
I have a couple more, like, these are more homework questions.
That's okay. Go for it.
Going through them, I was just writing the ones down that I didn't exactly understand how to do because
Fine,
either the
perfect.
solution wasn't just good or whichever. So
Okay.
one was chapter 20, number 7.
Okay. Chapter 20, number 7. So let me first share my screen again. So this is chapter 20. This is chapter 21. I go here. No, I go here. Chapter 20. Which one again? Number 7, you said?
7, yeah.
Okay. So it says the Trial Urban District Assessment, TUDA, is a government-sponsored study of student achievement in large urban school districts. TUDA gives a mathematics test score from 0 to 500. A score of 262 is a basic mathematics level, and a score of 299 is proficient. Scores for a random sample of 1,100 eighth graders in Dallas had a mean of 271 with a standard error, not deviation, but error of 1.3. A, we don't have the actual scores, but the use of the T procedure is surely safe. Why? So remember, the T procedure is robust, which means that it is easily, or it's easy for it to overcome issues like non-normality, skewness, possibly outliers. But for each hurdle that we have to overcome, the necessary sample size is a little bit larger. And the book talks about this, 15 or 30 or 40, whatever those numbers are. When you have 1,100, that is such a large sample size that it's surely enough to overcome any issues that might be there. So the reason why it's safe is because the sample size is very large. It's not that it's always safe. That's, small samples or skewness or outliers. These are all issues. But because of the robustness of the T procedure, with a large enough sample size, it overcomes all of those. So then it says using table C, give you 99% confidence interval for the mean score of all Dallas eighth graders. Be careful the report gives the standard error of X bar, not the standard deviation. So let's start by writing out the formula for the 99% confidence interval for X bar. It's going to be X bar plus or minus T star times S over the square root of N, correct? This is the formula for the confidence interval, correct?
Oh, I'm so sorry. I actually meant number 5. Sorry.
Well then, well, okay, so number 5. Only took you that long to realize, huh? All right. That's okay. I'm sure someone else appreciated what I did so far on that one if they ever watch it. Okay. You are testing the null hypothesis, H naught, where mu equals 100, against the alternative HA, where mu is greater than 100, based on an SRS, well, that's good, of 9 observations, so N equals 9. From a normal population, that's good too. And the T statistic is 2.5, and the degrees of freedom, of course, is 1 less than the sample size, which is 8. They don't have to give it to you, but they did anyways. And the question is, where does the P value fall? Well, 2.5 on my normal distribution table is 2.5 deviations to the right, correct?
Yes.
2.5 deviations to the right.
It's 2.5 deviations because of the T statistic being
2.5. That's exactly what the statistics are. It's how many deviations away you are from the mean. So we are 2.5 deviations from the mean, right?
Mhm.
Now, if I go to a table or use my calculator, I'm essentially computing the probability of being in that section. So let's take out my fancy dancy TI calculator and do a inverse, or sorry, do a T CDF, not the normal, but T CDF, and go from 2.5 as my lower to infinity as my upper, lots of 9, very big number. And degrees of freedom is 8. And I hit paste and I hit calculate, and it gives me a p-value of 0.0185. And 0.0185 is between 0.01 and 0.02.
If I were to do this on like the table, well, would I be able to?
Well, let's take a look. T table calculator. Let's take a look at what we can do here. Oh, I want an actual table. Let's go to images. Okay, so here we have a T table. So we go to 8 degrees of freedom, and we want a one-tailed T statistic. So I'm looking for 2.5, 2.5, 2.5. Oh, 2.5 will be right there.
I see.
So 2.5 would land between 0.01 and 0.025. So this particular table can only get to me within that region, 0.01 to 0.025. So this would not be the best one to use for the particular question that we did, because the question that we did, if it's between 0.01 and 0.025, how do I know it's not over here in this little section, right? Past the, past that area, right? You see what I'm saying?
I see.
So that would not be one that I'd want to use for this particular question, but in theory I could. Right? In theory.
So you recommend to use like the p-value calculator that we have?
Yeah, I mean, listen, the p-value gives you the exact value. The tables can only give you, an approximation. It's between here and here. But at the end of the day, we'd much prefer to, have the exact value if we could, right? Although, in theory, it at least it gives you a range. But, this particular homework, that range would not be good enough. And you can even see here, you have 0.025, right? I guess the question was to pick the two that are the best. So how do you know it's not between 0.02 and 0.025? There's no way of, well, there is kind of like a way. If I go back to that table, we know that 2.5, 2.5, actually it's, no, you can't do it because 2.5 is like almost halfway in between these numbers, right? You see what I'm saying? So very difficult to get a good approximation of that without really having a little deeper understanding of, I mean, if you look at the curve, we know that the further out you go, the more it drops. So a number that's halfway in between will have an area closer to the lesser number in this case and the greater number, but that comes from having a little deeper understanding, which it's okay if you don't have after I didn't have it as my first statistics class. It took time. These things come over time. So I would recommend the calculator. Does that make sense?
It does.
Okay, good talk. Good talk. I'm glad we're on the same page here. I feel good. Feel good. Oy.
I think that's it. I just have to practice how to determine p-values more, whether it be by table or by software. I think that's just what's tricky.
Yeah, that's the purpose of homework, right? The more homework we have, the better we get at these things. It's not just to torture you, although that's a nice little bonus for us as teachers, but it's to do exactly that. It's for you to get practice.
Is there a particular equation for p-value, or would we just use t to determine p-value?
Is there a particular equation? Well, it's the probability of being passed a number. And how do you get that probability? By a table or by a calculator. You don't do that by hand.
Mhm.
There's no, you can't plug it in by hand. Whether it's Z or T makes no difference. That's not something that can be done by hand. The mathematics does, when you get the formula for the normal is complicated enough. And when you try to do the appropriate mathematics upon it, it can be shown that it's not mathematically possible. And as such, the best we can do is numerical approximations that our calculator or computer do for us. So it's not that I don't want to, it's that it's literally not possible. Does that make sense?
It does.
All right, I'm gonna mute for a second because my sister's calling and she doesn't usually call now. I want to make sure everything's okay, okay? I'll be right back. Well, that wasn't as much as an emergency as I thought it was.
What happened?
My sister, the younger, called.
Adina?
Yes.
Yeah.
She needs my chemistry help for her son. That's the emergency. All my years of schooling, and I get to explain chemistry to a kid who doesn't pay attention in class.
May I ask a question?
Sure, go ahead. Oh, I'm still
Um,
recording. Oh my God. I'm still recording. I was going to pause it. Okay, go ahead.
The question is regarding chapter 21, number 3, and I've gotten to the point. I've did everything to the last section, and out of frustration, I ended up. I'm on my like 9th attempt.
Okay,
and
hold on.
all 4 options are incorrect.
Really? Well, let's take a look. Question 21, number 3. Let me share the screen. So, okay. Businesses know that customers often respond to background music. Do they also respond to odors? One study of this question took place in a small pizza restaurant in France on 2 Saturday evenings in May. On one of these evenings, a relaxing lavender odor was spread through the restaurant. On the other evening, no scent was used. The data gives a time in minutes that 2 samples of 30 customers spent in the restaurant and the amount that they spent in euros. So no odor, minutes spent, euro spent, lavender, minutes spent, euro spent. To access, okay. The 2 evenings were comparable in many ways. So we are willing to regard the data as independent SRSs from spring Saturday evenings at this restaurant. The authors say, therefore, at this stage, it will be impossible to generalize this results to other restaurants. Does a lavender odor encourage customers to stay longer in the restaurant? Examine the time data and explain why they are suitable for 2 sample procedures. So here's the things. We are going to investigate the time data. So T, 2 sample. Sample 1 is going to be minutes with no. Sample 2 is going to be minutes with lav. We're not pooling. It's, what was the question specifically? Do lavender odors make them stay longer? So we are doing a lavender 2 is greater than 1. That's a less than. 1 is less than 2, and we calculate. And we get a p-value, which is very, 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 very small. So because the distributions are reasonably symmetric with no outliers, and the samples can be treated as independent SRSs, the T procedure works well. True or bummer. So did you say true for that one?
Yeah, I'm
No.
on the last part of that, of the entire thing, like bottom of the page.
Bottom of the page.
Yeah, that part.
This part?
No. Yeah, you can keep scrolling down. There we go.
Well, so okay, so this is so this is the cent and no cent. So this is not the but what are we checking? We're checking against spending. Okay, so statistics T2 sample
Euro.
no Euro lab, right?
Yeah,
And what do we think? We think people spend more with lab, right? That the first is less than the second.
correct.
Okay, so the test statistic negative 5.95. That's what I have here, negative 5.95. My p-value, as you can see, with a number that small is very small, negative less than 0.0001, or in this case, less than 0.0005. And then the question is, what is your conclusion? Well, p-value very small means we reject the null hypothesis in favor of the alternative, that people spend more when there's a lavender odor. We have strong evidence that customers spend more when the lavender odor is present. What's the issue? Seems correct to me.
Yeah, I selected that option like 4 attempts ago, and it still said I was incorrect.
Perhaps it was something else that was incorrect, somewhere else in the problem.
No, so when Sapling says you're incorrect, it boxes in which exact one you are incorrect.
Why don't you, can you do it right now, even as your 10th, even if you get it wrong, and share it with, share your screen?
Yeah.
And then, if there's a problem with Sapling, we can always raise your grade.
So we have strong evidence that mean spending is larger when lavender is present.
Correct.
And I'm going to select that.
Wait, share your screen while you do this, please.
Oh,
Okay, I had to allow it. Go ahead. Okay.
okay. Can you see it?
We have some evidence, or we have strong evidence. A p-value that small is strong evidence. That's not some evidence. That's strong evidence. That's a very small p-value.
Oh, okay. I got another thing that's wrong,
Okay,
but I'll work on that.
no problem.
All right, but thank you.
You got it. I got to pause.